Okay, so for two variables, we uh, we forget to mention this topic. We have such, we call those things as a variable of variable. Okay, so those are also those are also a typical topic and useful topic. So for example, like x, suppose the landing value x follow uniform distribution between this like uh, this 0 to this, but this ending point can change. So like suppose like a 0 to y or 0 to theta. So this, we can call this parameter. This theta can change. This theta also can change. So theta, so we use just y. So this y also uniform distribution between 0 to 3. Okay, so here this x, we say x follow uniform distribution between 0 to y. And y also follow some other distribution. So let's say for uniform distribution between 0 to 3. Okay. So we can regard this x is a variable of another variable of variable. So we wanted to find the expectation Ex and Ey, or Ex and Vx. So we say that for Ex, so X can change, so we have to fix Y first. So this equal, we say this equal we have to fix the Y first. And this is a variable of y, right? Then we also need to just check average e. So we call those things as double e, double e, double e theorem. Some textbook call it double e theorem. So this just makes sense. Like if we want to find x, so we have to fix this y first, right? Then let the y change. So let's say, so this one, let's say. So what is this? For fixed y, what is x? So x from x uniform between 0 to y. So this, for this, we assume y is fixed. So then the mean is midpoint. So this is just half of y, right? Then find this expectation. So y from 0 to 3. So y is just half of 3, right? Half of 3. So we say this is 4 over 3. So for variance Vx, Vx, we have this, so we call this as law of total variance. So we have this formula V. Oh, okay. So maybe so Vy. So here Vy with x. Just let's say just let one fixed, like here, equal Vey with x fixed, and Ve plus Ev. We just say this is equal Ve thing fixed plus Ev. Okay. Okay. So let's say for this, let's say Vx. So we just go back to our problem. So this equal V is this x when y fixed, okay, and is v, okay, is v this x when y fixed, okay. Okay, so let's apply to this theorem to our problem. Let's say x when y fixed, this is, so because x is uniform from 0 to y, so e is y over 2, right? Okay, so plus, so this v, when y fixed, x is from 0 to y, right? 0 to y, so uniform distribution from 0 to y, and its variance. So for uniform distribution from A to B, variance is thus, like divided by 2 of B minus A. So we also can regard this as a formula. And for this, you also can easily to conform, right? So this V equal y b minus a, y minus 0, so y square over 12. Okay. So now we say, so what is so this equal, let's say this equal, so we put the coefficient outside is 1 over 2 squared, so 1 over 4 vy, so plus 1 over 12 y squared. Okay. Okay, so now the problem becomes easier. What is y? Y is uniform from 0 to 3, right? So it's vy equal 3 square over 12. Okay. What is y square? So we can find ey square directly, or we also can use the formula. Let's say we have this, like vy equal ey square minus ey square, right? So ey square equal vy is equal 3 square over 12 plus ey square. Ey is 3 over 2 square. Okay. Okay, so this is just the Vx. So such a problem, this is a very typical problem, is we say variable of variable. So if we have two variables, so typically this is like a x for some variable, but this variable have some parameter, like x for like a binomial, for normal distribution. So for normal distribution, we have mu and sigma, right? So we have those parameters. So if mu and sigma not fixed, mu and sigma also can change. Saying we need those formulas. Okay. Okay. So this is an example. Like okay. So we want to find ey, so we use double, right? Double. So here, when x fixed, so we need to find this first. Then when x fixed, so when x fixed is y is 25y, so saying this become like 25 is x. Okay. Okay. So for this problem, use the same problem. Like we want to find like what is we want to find what is vy, right? We want to find vy. So vy we have two parts. Vy equal v e y fixed x plus ev, right? We just remember this equal ve plus ev. Okay, ev y giving x or fixes x. Okay. Okay. Oh, I'm sorry. But anyway, like we forget to put this example 5.2a. But anyway, like if we understand this thing, we just here like is this so x fixed, so find y, right? Okay. So this is a discrete situation. Like x can be 0, x can be 0, 1, 2, 3. So for fixed x, what is y? So if x equal 1, like x equal 0, x equal 1, x equal 2, x equal 3. Okay, so then like this actually is just v y for giving x. So for giving when x equals 0, this v equals this. Like when x equals 1, this v equals this. Then this e is average for this. So this e equal those things multiply probability that x equals 0, x equals 1, x equals 2, and x equals 3, right? So we have this part. Okay. Okay. So here we have another example. Let's say the probability of a claim being filed is 0.1. So okay, so like for car insurance, this is just like file a claim means like car accident happen. So this car accident happen can be 0.1. Okay, so when a claim filed when car accident happened, but the damage is not fixed, right? So now the damage can change. So we say claim amount is exponential distribution, which means is 1000. Okay, so we want to find here what we want to find. So let y, let x be the number of claim and y be the payment. So we want to find like average payment EY and VY. So payment. So payment is when x equals 0. So number of claim is 0, then payment is 0. When x equals 1, so payment average payment is 1000. Okay, and when, so here when x equals 0, variance. When x equals 0, so y is 0, payment is 0, so variance is 0. So when x equals 1, when x equals 1 means when there is a claim, then the variance, this variance, so this claim, so this claim, payment, this payment actually follow exponential distribution, right? So mean is 1000. So we can say that this lambda equal 1 over 1000. Okay. So for exponential distribution, we have this, right? So let's say density function for exponential distribution is just lambda is negative lambda x. Okay, and for this landing variable, we have this, like x is 1 over lambda, and vx equal 1 over lambda squared. So this result we can confirm easily. Or if we wanted to take the actual exam, so those things you should remember. We can regard those as a formula. So let's say that here the variance for payment when x equal 1 means when claim have one claim, then mean is variance 1000 square. Okay. Okay. So let's say, so variance the average for so here so we can find let's say variance like this average for variance equal like a probability this thing happen. The variance can be 0, can be 1, can be this, right? The probability is 0.1, 0.9. Okay. Okay. So this is also an interesting problem or reasonable problem, right? Car accident happen. So we know that's happen or not happen. But when car accident happen, the damage can change, right? The damage is not fixed. Sometimes we have a minor damage. Sometimes we have a serious damage, right? So those damage, those loss or damage or payment, this is the landing variable. Okay. Okay. So for two variables or two variable distribution, we also can have variable transformation. Okay. Like for one variable, we say we have density function for x. Okay. So if y, so new variable, this y is like is a function for x, then density function of y, we just change x to y, right? So here equal the density function of x, we just change x to y. But here we don't forget we need to multiply dx dy, right? So this one we can say before it's always dx. By now we changing no dx, we changing to dy. So from dx to dy, we have this, right? Okay. Okay. So for double for double two variables, we can use the same idea. Let's say before we have x, y, we have density function for x, y. So now we have uv, like we have a new variable. U is, let's say, a function for x, y. V is a function of x, y. So we have a new variable uv, right? So then the density function for uv, so here we say this is x, y. So at the first we just change this x, y to uv. Okay, so uv, so here changing x, y to uv. So here we just solve for x and y, right? So for x we get x equal like u minus x1 uv, right? Okay, and but anyway, like we just changing everything to uv. So here just change those x, y to uv. Okay, and then don't forget this. Like so, we say before is dx dy. By now is du dv. So from dx dy to du dv, we need just like it, we need use dxy over duv, right? Just like one variable. But we do not have dxy. So if we have two variables, so we call this a partial derivative. So this we call this Jacobi determinant. So this we denote as a partial here xy over uv. So just regard x and y as a function of uv. Okay. So here we need to multiply this, like partial uv. Oh no, xy. They don't got confused. Xy partial uv. Okay. And there's a determinant. Oh, we also can say this is like a absolute value. So for one variable is also like a we should put this big. This is absolute value. If this derivative negative, then we should make this as a positive, right? Because it's this is density function of probability. Probability cannot be negative. So the idea quite the same, right? Changing everything to new variables. Then don't forget, like we need to change dx dy to du dv. So we need to multiply those Jacobi, right? Okay. So here we have such a problem, like okay, like so we have x1, x2. So now we have a new variable y1, y2. So y1 is this x1 plus x2. So y2 is this. Then new variables, or we just use transformation, a new density function, changing everything to uv. Oh no, change everything to y1, y2. Then don't forget, yeah, we still have this, right? So this one is just like partial x1, x2 to y1, y2. Okay, so we call this as a determinant of A. Okay, so the idea is the same, but here lots of calculation. Like at the first, we need solve x, x1, x2 in terms of y1, y2. So we can say we regard x1, x2 as the function of y1, y2. Saying we can have no. Where is v1? So here make it says here this is should is x1 actually, x1 y1. Okay, partial x1 as a function y1, y2. So x1 for derivative y1 is y2, right? So here, yeah, v1, v2 just x1, x2. Okay, so this problem I copied from textbook. Okay, so now I think we finished the topic for probability. Okay, so we say probability is a language for statistics. And so from probability, to statistics. The connection between them is called a centrally limited theorem. So what is centrally limited theorem? It's just this, like x bar follow normal distribution. So we are quite familiar with this result, right? So this is centrally limited theorem. So x bar is just x1 plus x2 plus xn over n. We say that this one will close, okay, will close to a normal distribution. Okay. Okay. So multiply by n, so we say like x1 plus x2 plus xn will close to a normal distribution, which means n mu, and standard deviation is radical n sigma. Or if we use a term of variance, we can say like mean is n mu, and variance just n sigma square. Okay, so here this is variance. So this is a centrally limited theorem. So we can say like so there's a problem in this centrally limited theorem is also very important in probability. So we can regard like for if we have two variables x1 x2, the problem can be very tough, right? We need a double integration. So if we have many variables, then those t those then like those t the same sort of, if we have many variables, then we have some trouble. Find probability or those things quite complicated. So we can regard this is very typical situation with the sum of those variables. So for this, we say this t will close to normal distribution. Okay. So instead, many things just come from normal distribution. Okay. So this is centrally limited theorem. Okay. So now let's say so this is the foundation for statistics, and this is just the connection between probability and stats. The centrally limited theorem is very important. So let's try to prove this. Okay. So let's mention proof. Okay. So proof. Let me see. Okay. So let's just mention this. Let's say proof of CLT. So CLT is so here we say each x1 x2 like okay, those x1 x2s of identical distributed, or basically they're the same. So we say those xi follow the same distribution with follow some distribution with mean is mu and variance or standard deviation sigma. Variance is sigma square. Okay. So what do we want to prove? We want to prove Since t will close to a normal distribution in mu and in sigma square, or take square root. If we're talking about standard deviation, then standard deviation is radical in sigma square, right? Okay. So how to prove this? How to prove this? So here we introduce, we introduce like a moment generating function. Okay, so now let's say how to show like these things follow some distribution. So we just wanted to show like for these things like how to prove, let's say question, how to prove x, y, those things, two things follow same distribution. So suppose we have two variables. We want, how can you say there's two variables follow the same distribution? Okay, so let's say if if we have, let's say distribution the same, if let's say from distribution, so let's say from distribution, we can like once we have a distribution, we can have Ex, right, and Ex square or Ex3. So we call those a moment. Okay, we denote this as mu1, mu2, mu3, like this. So we say mu k, we define this equal xk. So we call those a moment. Okay. So one distribution just have only one moment, right? Or one sequence of moments. Then let's go back. So if the moments are the same, so from this moments, then we can say distribution the same. So this is just like let's say for distribution or density, we just have a distribution is completely determined by density function or this function, right? So for polynomial function, we say for this polynomial function, like let's say this equal 1 plus 2x plus 3x squared plus 4x, suppose like, okay. Okay. So this polynomial, we determine those coefficients, right? And from these coefficients, we can just determine one function. Okay. Okay. So from this mu1, mu2, mu3, so we want like from these coefficients, we can define a function. So in general, we have this, let's say for any function. So polynomial function is the simplest function. So in general, for other functions, we can writing them in terms of we can change every functions as a polynomial function, right? So for example, we can say x exponential function, we can change this as a polynomial function, right? Okay. So those things, we call this a Taylor expansion, right? We can retain any functions in terms of polynomial function. Okay. So we say like in computer, computer just treat any function as a polynomial. Right? So in computer calculating, computer can only do those only can do addition, multiplication, and can only do those things. Right? So how can computer find ex? Just use this, right? Okay. So from let's say from those coefficients we can define the function. So let's say from this mu0 or mu1, mu2, mu0 is 1, 1, mu1, mu2, mu3. Okay, we define this function. Summation. So here mu k over k factorial and oh no, not is tk. Tk is part of the k equals from 0 to infinity. So such a function, we call this function moment generating function. So moment generating function. Suppose this is just we denote this as mt. Okay, so certainly related to the ending variable x, right? So this moment generating function means from this function we can generate all moment. So from this moment generating function we can find all its moment. So for this reason we call this moment generating function. So how can from moment generating function how can we get this moments? So this is just let's say we say this function case derivative. Let's the case derivative then when t equals 0, we get just equal mu k. Okay. Okay. So how to prove this x y, these two things has the same distribution. So we say if the moment generating function, if moment generating function for x and moment generating function for y, if this moment generating function is the same, we say x and y follow same distribution. Okay, or we say x and y are identically distributed. Okay. Okay, so now let's say, so we just wanted to say this t, this t's moment generating function and this normal distribution has the same moment generating function. Okay. Okay. So here, and so here, this moment generating function. So we find this moment generating function. This moment generating function. At first, we say moment generating function equal this, right? equals summation mu k over k factorial tk. This is the definition for moment dependent function. So what is mu k? What is mu k? Mu k is the case moment. So we say case moment is thus, like we put k factorial here, k factorial tk. So mu k, what is mu k? Mu k is equal to exk. What is exk? Is this exk equals thus. Let's say what is exk? Yeah, what is exk? So exk is equal to xk f x dx. Okay, right? Okay, so this one equal, we can put this, put the summation to here as this just equal negative infinity to positive infinity. So put this into like k factorial and tk xk and f x dx, right? And summation k equals 0 to infinity. Okay. So what is this summation? So this is equal to txk over k factorial. So we know this just equal, let's see. So this like xk over k factorial summation. This is just x. So this is just equal tx and fx dx, right? Okay, so this one is just the expectation of tx. Okay, so moment general function is just equal we like so here x landing variable, t is a, we can regard t by now, we can regard t is fixed, but the t just a parameter, t can change, right? So for fixed t, etx its expectation just uses formula, right? Okay, so now we want to find for a normal distribution. So if x follow normal, so what is its moment general function? Okay, so x follow normal, so density function we can check density function is some coefficient, right? So simplest one just like is negative x squared, right? So those is a normal distribution, like goes down on both sides. Okay. Okay. So this is 0, right? And if f(x) just like that, so what is moment general function? Let's check. Let's check standard normal. Okay, standard normal. Maybe we need the moment general function for general normal. So let's review that. If x follows normal, then the density function for x is as coefficient of square root of 2 pi sigma, then e negative 2 sigma square x minus mu square. Okay, so that's the function thus. So roughly just like x squared, so sigma squared is just coefficient, right? Okay, the center is mu, but anyway, like if x is there, so how can we find e? So we forget this constant. So let's say what is e? What is moment generating function for normal distribution? For normal distribution, so this equal, let's say, negative infinity to positive infinity. So e dx, e negative x squared dx. Okay. So this one we can put this as this, right? Negative infinity to positive infinity, e negative x squared plus tx. Let's say x squared plus minus tx, then plus t squared over 2, t squared over 4. So here, let's say this just make a complete square. Let's say maybe put it to here, tx minus x squared. We can change this as x squared minus tx plus, so here half of t, so t squared over 4. So then plus t squared over 4. Okay. Okay, so this is just equal negative x minus t over 2 square plus t square over 4. So this integration e tx minus x squared integration, so equal, so is this, we can put this constant outside actually. For then e here is negative x minus t over 2 square dx. So use substitution, which is x minus t over 2 as new variable, as u. So this is just equal t square over 4. Then this integration, so have nothing to do with t, right? X minus just u square negative u squared du, and this is a constant. So this is just a constant. So we say moment generating function no normal distribution is just like that, e t squared over 4, or multiply some constant. So forget the constant. So we know moment generating function for normal distribution we find. Then we just wanted to prove this moment generating function for t is thus, so this t will also close to those things, close to like close to like t, like e t square, e t square over some coefficient, right? Okay, so here, so we say like if t equal x1 plus x2 plus x plus xn, then moment generating function for t is e t So this I'm sorry, t, so then x1, tx2, like that, right? So we say this is just a multiplication. So so this become like I'm sorry, txi. Okay, so moment generating function for txi, so we know this equal moment generating function. So this is a mu 0, like xi's moment generating function, right? So mu 0 is 1, so mu 2, mu 1, so mu 1 is mu 1 is a mu, right? So mu 2, so we here, so we can make some simplification. We just say, oh, we just assume this t1, t2, those x1, x2 follow. We just can assume like mu equals 0. Because if mu is not 0, we can minus mu, right? x1 minus mu, x2 minus mu. So okay, so t minus n, we just use substitution. We can make things simple. So t become t minus n mu, right? So we just need to find t minus n mu. We just consider t minus n mu. So here, but anyway, like we assume, we just consider simplest case, like x1, x2, they follow a normal distribution, or they follow a distribution with mean is 0. So we can always simplify this to be 0. And we also can simplify the sigma as 1, because like we just divide by sigma, we just consider this, then we can change this to 1, right? So we can assume those xi, each xi follow this distribution, follow a distribution with mean 0, standard deviation is 1. Okay, so we can prove this. So we just check this t is that moment generating function. Yeah. So okay. So this equal, if this is 0, 1, so this means like okay, go back. Here's 1. So mu, so minus mu, minus, no, plus mu 1t, so mu 1 is 0. Then plus mu 2 is 1 over 2, then here t squared. Then have those things, right? Okay, so this equal, so we just check the case when t very, very small, so this is just like here let's say 1 over 2. Oh, we say variance, yeah. So let's say, so variance. So here we need to check there's t divided by n, yeah. So here we little bit algebra, right? We just this equals 0. So we have an n here, so we don't like this n. So we just check t over n. Yeah, t over n. Or what t over radical n. We just need to check t over radical n will follow this 0 and sigma radical n. If we take a radical, this is, we just need to check this. We just need to prove this, right? T over radical n is this. So t over radical n, so there's a coefficient have a radical n. So here we have radical n squared. So radical n squared is just n. Okay. So we have this. n t square. So this n's power. Okay. Okay. So when n goes to infinity, very large, so we find this one follow. So this one, we do not have enough space. So this one will close to e t square over 2 or t square over 4. Okay, so here what is e? So let's leave it, put it to here. So we say what is e? E is this limit. So 1 plus 1 over n's power is e. Okay, so here 1 plus 1 over 2 n t square over n's power. This one will go to, let's say, this one, we just regard this as 1 over n. So this one is 1 over, we put this t square as like 2n over t square. Okay. Okay. This is 2n over t square. Okay, so this is n's power, so we say t square over 2. Okay, so this will goes to, let's say, this part goes to e. Okay, this part goes to e, then this part goes to, let's say, I'm sorry, goes to e t square over 2. Okay. Okay, so we say, oh, moment, there's t, there's moment of t will looks like e t square over some coefficient, like t square over 2 over 3. So this we prove those things. Moment generating function is same as normal distribution, right? So we say the t, the x1 plus x2 plus xn will follow such normal distribution. So this is essentially limit theorem. Okay. Okay. So with this thing, central limit theorem is a connection or bridge between probability and stats. So now we can move to statistics part. Okay. Okay. So we can stop here.